Hello everyone, it is my honor to present my research results here. I am CHANG-HUA Lin. Today, the topic of my presentation is Design and Implementation of a Diagnostic System for Lithium Battery Module based on Sinusoidal Loading Technique. Outline. I will separate this presentation in 5 parts. First, Introduction. Next, I'd like to talk about the hardware of the proposed diagnostic system, and then, I will explain the model analysis of the sinusoidal load. Moreover, some simulation and experimental results will be verified. Finally, the conclusion of this paper. Recently, more battery-powered applications have been developed, such as mobile, electric drill, electric bicycle, electric scooter, electric vehicles, and energy storage system. Batteries are really convenient for people and influence people's daily life. Therefore, many interesting research papers regarding lithium battery have been published and attracted more attention. In general, battery modules, which are the power source of electric vehicles, determine the endurance ability of the vehicle and some vehicles' performance. The battery modules used in electric vehicles are composed of hundreds of battery cells, even more than thousands of battery cells in the battery module, like TELSA. A battery pack of TELSA III include 12 battery module. Each module has 240 cells, that is to say, totally up to 2,880 cells. Even if carefully sorting, among each cell still may have differences in electric characteristics that become more apparent with time. Excessive differences can reduce the utilization rate of battery power and then damage the battery module or even cause dangerous accidents. To get the practical electrical characteristics of the battery module, many battery test systems are gaining more and more attention in the market for test instruments, especially with energy recovery or energy recycling. However, almost all battery test systems are too bulky, expensive, and not portable. In this study, we want to construct a portable and low-cost battery test platform. Next, I will introduce the hardware of the proposed diagnostic system. This slide shows the system architecture of the proposed diagnostic system, which consists of a sinusoidal load, a MCU, a USB module, FT232, an auxiliary power circuit, a signal, voltage, current and temperature capturing circuit, and a DC level offset circuit. In this study, the sinusoidal load is a key part of the proposed diagnostic system. Actually, the sinusoidal load can provide high-frequency loading current for the tested battery module. The sinusoidal loading current with wide-range slew rate is closer to the practical work conditions. Moreover, the sinusoidal load outputs dynamic loading current within the positive semi-cycle for diagnosing battery characteristics and recycling the extracted energy within the negative semi-cycle. Then, I will explain the model analysis of the sinusoidal load. The proposed sinusoidal load is developed from the Class E topology, which consists of 2 inductors, 2 capacitors, and 1 power switch. In this study, a tested battery module is used as the voltage source Vs. To generate the required bidirectional current behavior, the modified Class E circuit structure is employed. After simplifying, we can get an equivalent circuit shown as Fig. F equals 150 kHz. To approach the practical work situations, a GaN switch is employed to generate high-frequency loading current, and the parasitic capacitance model is also considered as shown in Fig. B. Moreover, the switching frequencies 140 kHz or TZ-O and E150 kHz of the sinusoidal load is varied to keep the preset loading current amplitude of V's changes. Based on the above design, the inductor current IL is almost symmetric waveform in each half cycle. The key waveforms of the proposed sinusoidal load in a switching period is shown as this slide. The circuit operation in a switching period is divided into 5 modes. In this mode, both the switch S1 and the diode D2 are off. In steady state, all of the resonant components include the resonant inductor L, the junction capacitance CD, the parasitic capacitance CDS, and the resonant capacitor C. The equivalent circuit is shown as Fig. O, which can be simplified as Fig. B, where Sec1 is the resonant capacitance of the equivalent circuit. Both the corresponding equations of the inductor current and capacitor voltage are listed as below. In this mode, as you can see, the initial value IL, T0, equals 0. The sinusoidal load current just start to rise and draw energy from the battery module during the positive semi-cycle. When T equals T1, the switch S1 is turned on at this moment to end this mode. At T equals T1, the switch S1 is turned on. The resonant capacitor's voltage is still at negative value, that is to said, the diode D2 is also turned off. The equivalent circuit are shown as Fig A, which can be simplified as Fig B. Both the corresponding equations of the inductor current and capacitor voltage are listed as below. In this mode, the sinusoidal load is still drawing energy from the battery module during the positive semi-cycle. When T equals T2, the resonant capacitor's voltage Vc, T, rises to 0, and this mode is ended. During this mode, the resonant capacitor's voltage continuously rises, and higher than 0, the diode D2 is conducted, and the switch S1 is still on, and then the resonant inductor L is magnetized by the voltage source Vs. Therefore, the IL, T, is rising linearly and the electrical energy, extracted from the battery module is stored in the inductor L. The equivalent circuit is shown as Fig A, which can be simplified as Fig B, and the corresponding equation of the inductor current is listed as below. In this mode, the sinusoidal load is continuously drawing energy from the battery module during the positive semi-cycle. When the switch S1 is turned off, this mode is ended. In this mode, the switch S1 is turned off, the inductor current IL, T, decreases to 0. The resonant capacitor's voltage Vc, T, resonates to a positive value. Therefore, the diode D2 keeps on state, and the resonant inductor L resonates with CS and C. The equivalent circuit is shown as Fig A, which can be simplified as Fig B. Both the corresponding equations of the inductor current and capacitor voltage are listed as below. In this mode, the sinusoidal loading current resonates to 0, that is to say, stop drawing energy from the battery module at T equals T4. When T equals T4, the resonant inductor current IL, T, decreases to 0, and this mode is ended. In the final mode, the switch S1 is still off, the diode D2 is also off. The resonant inductor current IL, T, resonates from 0 back to 0. Therefore, the resonant inductor L resonate with CD, CDS, and C. The equivalent circuit is shown as Fig A, which can be simplified as Fig B, and the corresponding equations of the inductor current and capacitor voltage is below. In this mode, the sinusoidal loading current is reversed to negative value by using resonant behavior, that is to say, start to recycle energy to the battery module. As you can see, when T equals T5, the resonant inductor current IL, T, resonates to 0, this mode is ended, and a complete cycle analysis is also finished. This slide shows a flowchart of the proposed diagnostic system to conduct system integration and management. This slide shows the implemented human-machine interface, which is programmed by C-Pound based on Visual Studio. You can key in some battery information. Preset protection conditions, display the monitoring parameters, V, I, T, and the related estimation value, such as state of charge, SOC, state of health, SO, of the tested battery module. OK. In this section, one will show some experimentations. When the battery-powered device or electric vehicle is powered by a battery module, the actual load current is irregular or non-periodic. Therefore, it is not easy to simulate the practical working current of the power battery for online test. Due to the inherent wide-range slew rate characteristics of the sinusoidal current waveform, which is suitable for simulating the work conditions. Next, we will demonstrate some experimentations by using the proposed sinusoidal load. In this study, a lithium battery module with 18,650 packages is tested to verify the proposed diagnostic system. A lithium battery module having 12 cells in series connected is served as the test target, and its specification is listed here. This slide shows the simulated and measured current waveforms of the proposed sinusoidal load. Enter C rate equals 03 C while the switching frequency is 150.5 kHz. All the simulation and experimental result verify the sinusoidal current waveform is the same as the theoretical prediction. This slide shows another test condition, where the C rate is up to 1 C while the switching frequency is adjusted to 144.6 kHz to meet the preset C rate level. All the simulations and experimental results still meet the theoretical prediction. And then we are going to show another experimentations. In practical work situations, the battery module voltage will decrease with load consumption. To avoid the decay of the loading current amplitude, variable frequency control is used to keep the preset current amplitude of the sinusoidal load. The left side fig is measured under the battery module voltage of 50V. If the battery module voltage decreases to 30V shown in the right side fig, the loading current amplitude still is the same as the left side one. And we can see, the switching frequency is changed from 149.7 kHz to 148.8 kHz. At this slide, we shows another test condition, where the C rate increases to 1 C. The left side fig is measured under the battery module voltage of 50 V. If the battery module voltage decreases to 30 V shown in the right side fig, the loading current amplitude is still the same as the left side one. And we can see, the switching frequency is changed from 147.1 kHz to 142.2 kHz. Finally, we will calculate the energy recycling rate by integrating the area of the loading current waveforms. Actually, it is clear that some differences between the positive semi-cycle and the negative semi-cycle, i.e., the energy drawn from the battery during test procedure cannot be recycled completely. In this slide, when C rate is 0.3 C, the integration value of the positive semi-cycle Q1 is 798.84, and the integration value of the negative semi-cycle Q2 is 700.62, so the recycling rate is 87.71%. That is another test condition. When the C rate is increased to 1 C, the recycling rate decreases to 80.52%. It is apparent that most of the unrecyclable energy is consumed on components and resulted in power losses. Although the proposed sinusoidal load cannot recycle all of the drawn energy from battery module, it is still superior to the traditional battery tester. This slide shows the prototype of the proposed diagnostic system. It is really compact, low cost, and pro-table. This slide shows the proposed function of programmable loading current. Both the amplitude and duration of the loading current can be programmed. According to the test requirement, user can directly edit these parameters of the loading current from the HMI of the diagnostic system. Finally, I would like to conclude today's presentation. A diagnostic system for lithium battery module based on sinusoidal loading technique is designed and implemented. The proposed sinusoidal load not only provides wide-range slew rate loading current for approaching practical work situations, estimates SOC, but also recycles the extracted energy every cycle without any additional grid-tied equipment or backup battery. This system exhibits compact topology, low cost, and closer to the real work conditions. Finally, the recycle rate of the electrical energy during test procedure is verified by the experimental results. That is my presentation. Thank you for your attention.